Hello, this is the filtration chamber system presented by Group ME22, consisting of Susie Copus, Anna Havrilesko, and Jocelyn Manson. To begin, this project is sponsored by Aceman LLC, which is a small business specializing in the design and manufacturing of orthopedic surgical devices through additive manufacturing. Aceman creates custom fixtures such as hip replacements or compression plates using MRI-compatible, X-ray transparent, and cost-effective composites aiming to expand access to advanced medical devices in undeserved regions. Aceman is currently developing a 3D printer, as shown here on the left, designed to print orthopedic limbs using a mixed carbon fiber and resin filament in a heated chamber. Because this filament releases ultrafine particles and toxic fumes, a filtration system is necessary to ensure operator safety and maintain the print quality. Our goal was to design a filtration chamber capable of removing both particles and volatile organic compounds, or VOCs, while also withstanding the high operating temperatures required for Aceman's printer. Extensive research was conducted into filter types and existing filtration designs to meet these needs. However, none of them are currently designed to withstand such temperatures. After researching, each team member created initial design concepts, exploring different layouts for sensors, ducting, filters, doors, and chamber orientation. Shown here are the preliminary concepts by Jocelyn as shown on the left, Susie as shown in the middle, and Anna as shown on the right, which we later combined into the final CAD design. Here we have our 3D CAD model of the final design, which includes an expansion and contraction system, real-time monitoring through sensors, a filtration system for both particles and VOCs, secure ducting attachments, insulation for temperature control, and a maintenance door for easy filter replacement. Other than the components, the materials for the chambers, expansion, and contraction needed to have a chosen material. So we performed a materials analysis using the Granta EDU Pack software provided by the school. In the end, aluminum 6061 was chosen for its high service temperature, low cost, low thermal expansion, and good shock resistance. After the material analysis, we then conducted technical analyses using ANSYS on the most critical part of the design, which was the brackets. On the left shown is a thermal analysis, while on the right is a static analysis, where 1/4 symmetry was used. It was confirmed that the system would remain structurally sound under operating conditions, as both strengths in the end fell below the yielding strength of the aluminum. After performing the analyses, the final components were purchased and assembly of the prototype began. Here you can see the main parts coming together based on our CAD model with the chosen metals and the chosen components. We also purchased the final sensors and created the final circuits where we integrated them with an Arduino board to give operators full system control and monitoring. To monitor and control the sensors, we used Arduino codes. Shown here are 2 sensor tests performed using working codes. On the left is the VOC sensor used with acetone to find the parts per million of the fumes. Then, in the middle, the thermocouple was tested to ensure that it read room temp and increased when in contact with human skin. On the right are the devices used to test the sound of the system, the airflow, and a graph to calculate the pressure based on that airflow. These were all used to test the other sensors for accuracy. In the end, we were able to create a physical prototype with working sensors. Thank you for your time, and we are excited to see this system contribute to Aceman's innovative 3D printing work.